Hello everyone and welcome to lecture 7 on this introduction to inorganic chemistry. And we really come to the end of the introductory sessions for this lecture series. We've talked a lot about the structure of inorganic materials. We focused a lot on these kind of large crystalline lattices. And we've even considered some of the energetics of bonding in these systems. What we haven't spoken about is how we determine the structure of these compounds. And that's a very important part of inorganic chemistry. So what I would like us to do today is to consider some key physical techniques that are used in inorganic chemistry, and indeed with the express aim of trying to determine the structure of a compound. And I would like us to consider ways in which we can use the correct technique for sample analysis. So, for example, if I want to determine the structure of a crystalline material, I need to know what kind of techniques I have available to me in the inorganic chemist's toolkit to be able to do just that. Now, in inorganic chemistry, you tend to apply multiple techniques when trying to work out the structure of a material. So these techniques may complement each other and ratify results that you've obtained with one of the techniques. And there are lots of techniques to consider, all vary in terms of complexity and cost. Some are just too costly really to use. But one common theme that they all have, or that many of them have, is that they rely on the interaction of electromagnetic radiation with matter. Now, more often than not in inorganic chemistry, you will see that this spectrum of the electromagnetic the region of the electromagnetic spectrum that is used is the X-ray region. But if you think about all of the techniques that you've come across in your studies in chemistry up to this point, there are lots of different regions of the EM spectrum that are used. So you've used ultraviolet visible radiation, you may have used infrared radiation, or you may have studied the use of infrared radiation when you're trying to work out the functional groups present in a material, for example, in FTIR analysis. And indeed, you'll be doing this, or will have done this, in the laboratory as part of the first year laboratory program. Now, this will be studied in far more detail in the second year, but I think this is an important part, or a good place to introduce the idea of diffraction. So you'll study this next year with Andrew Fogg in more detail, but diffraction methods are key in inorganic chemistry. They're incredibly important for the determination of the structure of compounds. And you can look, if you look in publications, then you see that diffraction has actually been used to determine the structure of around about 250,000 different inorganic and organometallic substances. That's before you even consider its application in biology and biochemistry and other areas of the chemical sciences. What we use diffraction methods for then is to pinpoint the locations of atoms and ions that make up a solid compound. So what we gain as a result of diffraction is a description of the material in which we are able to interpret things like bond lengths, bond angles, and positions of atoms within the crystalline structure relative to other atoms. We get a complete picture then of the unit cell of the crystalline solid, which we've spoken about in great detail. Now, very simply, what we are doing in an X-ray diffraction experiment is to take our sample and irradiate it with a collimated beam of X-rays. What we mean by that is a very thin beam or a very narrow beam of X-rays, and we irradiate our samples. And in this case, we'll focus on the example of a crystalline solid. And when those X-rays strike the atoms within our sample, they are diffracted or scattered by the atoms. And what we gain then is a diffraction pattern. And you can see that very nicely in the diagram that I show you on the right there. And from that diffraction pattern, we are able to calculate information about the relative positions of atoms within the lattice, and indeed again infer things like bond lengths and bond angles. So it's an incredibly powerful technique in terms of structure elucidation for inorganic materials. And if you think about the wavelength of X-rays that we're using X-rays with a wavelength of about 100 picometers, and that falls very nicely with the characteristic distances between bonds in the crystalline materials that we're investigating. So these X-rays are very well scattered by atomic centers in crystalline substances. Now you can think of the scattering of an X-ray or the diffraction of an X-ray as being equivalent to reflection from two adjacent parallel planes of atoms which are separated by a distance d. So all this is two parallel planes of atoms within my crystalline material, and we're looking at an individual scattering event here. And as the X-rays strike these two individual planes of atoms, they are reflected or scattered or diffracted. Now, when the incident X-ray waves strike these two planes of atoms, we can get both constructive and destructive interference. We're interested in the angle at which constructive interference occurs because that produces a nice maximum in our diffraction profile. And we can relate the wavelength at which that occurs to the spacing in between the lattice planes. And you can see that you can do that by the equation n lambda equals 2d sine theta. So we can get an appreciation of spacing within the lattice just from the application of a very simple equation, and that's known as Bragg's law. What you see then is a diffraction pattern. The raw diffraction patterns are shown at the top of the image there, and through a radial integration, we gain a final diffraction pattern that shows peaks, or what we call diffraction maxima. And each one of these maximums or reflections occurs at an angle that corresponds to a different separation of planes of atoms. You can see that by analysing the individual peaks, we can start to get very detailed information about the spacing and orientation of atoms within our crystalline sample. Now, when you use X-rays and X-rays are scattered by a crystalline lattice, they are scattered or diffractive in proportion to the number of electrons that surround the atoms within the crystalline lattice. What that means fundamentally is that X-rays are scattered by the electron cloud of the atoms within the crystalline lattice, and therefore X-ray diffraction is very sensitive to the presence of electron-rich atoms. Consider the two compounds that I show at the bottom of the screen there. Sodium nitrate with just sodium, nitrogen and oxygen, very light atoms, and the diffraction pattern that is displayed would be fairly even between diffraction from sodium, nitrogen, and oxygen. If I was to look at the compound in the bottom right of the slide there that contains lead, oxygen, and hydrogen, because X-rays are scattered by the electron cloud, the scattering pattern from that compound would be, and any structural information that we can gain from that would be heavily dominated by lead, because it's much heavier and it has many more atoms surrounding the atomic center. So we'd very easily be able to point out the position of lead in our crystal structure. It would be much more difficult to interpret that data and try and work out where oxygen and hydrogen sit within the crystalline structure, because, as I said, the scattering pattern or the diffraction pattern will be heavily dominated by lead with the higher number of electrons. Now, powder X-ray diffraction is typically used to determine lattice parameters. So we're talking about unit cell parameters here, bond lengths and that kind of thing, and lattice type. So we can look at the peaks and very easily work out the kind of lattice that we have. And that powdered sample contains, it's not just one single crystal. It's a collection of a very large number of small crystallites. Think about a teaspoon of salt, which is sodium chloride. Each one of those tiny grains of salt is a different crystallite. A teaspoon of salt isn't one single crystal, it's a collection of lots and lots of crystals. We would grind that up clearly if we were to use it in powdered form and investigate the structure of sodium chloride with X-ray diffraction, but even still, there would still be a very large number of small crystallites in there. It's not one single crystal. Each one of these crystallites has a dimension of about 0.1 to 10 microns, and of course, when we put them in a vessel to measure them, they're all oriented at random. So therefore, the X-ray beam, when it strikes that, what we call a polycrystalline sample, is scattered in all directions. And indeed, at some of these angles, given by the Bragg equation, that constructive interference occurs. What you gain then is a cone of diffraction intensity. Just like the image I show you on the right there, because these X-rays are scattered in all directions. Each of those cones consists of a set of very closely spaced diffracted X-rays, each one of which represents diffraction from a single crystallite within that sample. Now, a powdered diffractometer will use an electronic detector, to measure the angles of the diffracted beams. And we scan the detector around the sample along the circumference of a circle, as you can see in the right-hand image there, and that cuts through that diffraction cone, and we can record the intensity of these diffraction maxima as a function of the detector angle. So here's a little question to consider. titanium dioxide exists as several polymorphs, the most common of which are anatase, rutile, and brookite. The experimental diffraction angles for the 6 strongest reflections collected from each of these different polymorphs are summarized below, and you can see them there. The powder X-ray diffraction pattern collected using 154 picometer X-ray radiation from a sample of white paint known to contain titanium dioxide in one of those polymorphic forms is also shown below on the right there, and you're asked to identify the titanium dioxide polymorphs present. So have a look at the peaks that you'd expect for rutile, anatase, and brookite, and see if you can match up the peaks from one of those polymorphs, or both polymorphs, or 2 polymorphs rather, with the diffraction pattern that you see on the right. Now, if we are really interested in not working out sort of lattice type or the polymorphs that are present in a sample, if we're really interested in obtaining a fundamental description of the structure of inorganic solid, then we will be interested in single crystal X-ray diffraction. And having a single crystal of a compound, assuming you can grow a single crystal of a compound, is important if you want really definitive, highly accurate information about the molecular structure and extended lattice structure. So we really want to dig down into the detail of the atomic structure of a crystal. Then we need really a single crystal. And this is super important in the pharmaceutical industry when you're talking about the structural elucidation of proteins. So if you think about the importance of proteins in the pharmaceutical industry, it's very important for pharmaceutical companies and research institutes to elucidate the structure of proteins that modulate disease. So they're able to design drugs that are able to bind with proteins and either inhibit or promote various biochemical processes that are modulated by that protein. It's critical that you have a single crystal of a protein in order to work out its structure through diffraction methods. And the same is true for inorganic solids. You're limited, of course, by the fact that you may not be able to grow a perfect single crystal of an inorganic solid or a protein. In single crystal X-ray diffraction, that single crystal is rotated around 3 orthogonal directions, and you use something called a 4-circle diffractometer and a detector to measure the X-ray beam intensity as a function of that diffraction angle. Now, the analysis of the diffraction data that comes from single crystal X-ray diffraction is an incredibly complicated process. You're looking at locations and intensities of many thousands of reflections. There's an example of an X-ray diffraction pattern on the right there from a single crystal. And trying to work out the locations of atoms from that information is incredibly complicated. Historically, this would have had to have been done by hand with a series of complex calculations. Fortunately, there is a vast improvement and advances in computational power that now means that computers can do a lot of that work for us. Now, modern X-ray diffraction studies tend, especially the single crystal X-ray diffraction studies, are performed at synchrotron sources. And you can obtain much more intense beams of X-rays by using synchrotron radiation. And what happens here is that you accelerate or you circulate electrons very close to the speed of light around a storage ring. And tangentially away from the circulating electrons come X-rays, or Bremsstrahlen we call them, very intense X-rays. And you can use those X-rays to measure the structure of compounds through diffraction. There are two major synchrotron sources in Europe. The first is in Oxford, at the Diamond Light Source, and that's shown in the bottom right there, just outside of Didcot in Oxfordshire. And the second is the ESRF, and that sits in a far more glamorous location at the foot of the Alps in Grenoble. There are some major benefits then to using X-rays that have been produced by a synchrotron source. The intensity allows the structure of very complex molecules to be determined. Because the X-ray beams are so intense, you can get away with much smaller samples. So think of the implications that has for single crystal X-ray diffraction, where it's often very difficult to grow a single crystal. And if you can grow a single crystal, then you only really can grow them in very, very small sizes. So you can get away with 10 by 10 by 10 microns for single crystals at a synchrotron source. A lab-based X-ray diffractometer simply doesn't have the intensity of X-rays to be able to usefully obtain any structural information from a crystal of that size. And at a synchrotron source, again, because of their high intensity and the flux, that is protons per second, of X-rays that strike the sample and can be detected by a detector, data collection is extremely rapid, so tens of seconds, as opposed to in a lab source, which may take minutes or even hours to gain data. That is an example of an X-ray diffractometer that is at Diamond Light Source in Didcot. Very complex piece of machinery. Now, if you can have X-ray diffraction, then you can have neutron diffraction. And subatomic particles like neutrons and electrons, they travel at suitable velocities for diffraction experiments, and they have wavelengths, suitable wavelengths, and are able to undergo diffraction by crystalline inorganic compounds. You can generate neutron beams of the appropriate wavelengths by moderating them. So you produce neutrons through either a nuclear reactor or through a process known as spallation. They come out of those processes at a very high energy, so you've got to moderate them. Usually you pass them through something like methane or water to lower their energies. In a spallation source, neutrons are essentially chipped off nuclei of heavy elements by an accelerated beam of protons. So usually you would accelerate a beam of protons and hit a tungsten target and chip off nuclei, chip off neutrons from the tungsten nuclei. And we have a spallation source in the United Kingdom. Again, it's right next to the Diamond Light Source in Didcot in Oxfordshire, and it's called the ISIS spallation source. Right next to the ESRF in Grenoble at the foot of the Alps then is a nuclear reactor source. So we are using neutrons from a nuclear reactor source to also characterize materials, and that's called the Institut Le Langevin, or the ILL. The instrumentation for measuring neutron diffraction patterns is very similar to the X-ray diffraction setup. The scale is much larger though, because you need huge international facilities. You basically need a nuclear reactor or a linear accelerator to generate the accelerated protons. And therefore neutron diffraction as a technique is much less routine. It's not the go-to technique, and tends to be used in cases where X-ray diffraction has failed. The advantages of using neutron diffraction over X-ray diffraction is that neutrons are scattered by the nuclei of an atom. So think how that compares to how X-rays are diffracted. X-rays are scattered from the electron cloud. So neutron diffraction is often very sensitive to structural parameters that complement X-ray diffraction, i.e. Neutron scattering is not dominated by heavy elements. So it's very good for the lighter elements such as oxygen, nitrogen and sulfur. And you can also, neutrons are also scattered by unpaired electrons, so you can also gain information about the magnetic properties of a material. Now, another important area of the characterization of an inorganic compound is microscopy. So that involves the viewing of materials. Usually we're talking about solid state materials on a scale which is smaller than the human eye can resolve. And I'm sure everyone has used visible microscopy at some point, but there are some other key methods to study the structure of inorganic compounds. They are electron microscopy and scanning probe microscopy. Scanning probe microscopy can be split into two further techniques, scanning tunneling microscopy and atomic force microscopy. And both of these techniques allow the 3D structure of a surface to be analysed by using a very sharp pointed probe that is brought into very close proximity with the specimen surface. And that probe is moved across the specimen surface, and the deflection of that probe is monitored, and a picture, an image of the surface structure can be built up. So in scanning tunneling microscopy, an atomically sharp tip is scanned around about 0.3 to 10 nanometers above the sample, and the tip is held at a constant potential or height above the sample. The tip itself is conductive, and those electrons that are in that conductive tip can tunnel through the gap with a probability that is related to essentially the distance from the surface. So you can build up a picture of the surface of the structure based on the tunneling of electrons. And there is an image of a scanning tunneling microscopy experiment. So that's a high resolution image of the surface of an inorganic material. You look at some recent papers in this field, you can see that you can actually get incredible resolution with this technique. So you can, with very powerful scanning tunneling microscopes, you can examine surfaces at really an atomic level. Atomic force microscopy then is a similar technique. It contains a tip which is moved across a sample. It doesn't touch the sample, but it sits very, very close to the surface of the sample. It's moved across the surface of your inorganic compound, and the tip interacts with atoms in the surface of your inorganic compound through intermolecular forces. And the tip is either deflected or attracted towards your sample based on those intermolecular forces. And you can bounce a laser off the surface of the tip and work out the structure of the surface. And you can see an image at the bottom there for an AFM experiment on an inorganic compound. Electron microscopy then is also a very powerful tool. It's essentially just a very powerful microscope, and it operates in a very similar way to an optical microscope, but it uses electrons. The electrons are being charged are focused using electric and magnetic fields, and there are two key types of electron microscopy: transmission electron microscopy and scanning electron microscopy. TEM, transmission electron microscopy, the electron beam actually passes through the sample and is imaged on a phosphorescent screen, whereas scanning electron microscopy, SEM, that beam is scanned over the object and the reflected or the scattered beam is imaged by a detector. It's a very, very powerful microscope, and the resolution is dependent on how sharply you can focus that incident beam, how quickly it's moved over the sample, and how much the beam spreads out onto the sample before it's reflected. So conducting samples are imaged very easily with SEM. Typically, you can get features with dimensions of 1 micron or less, so you can image things like bacteria, single bacterial cells. Although with modern electron microscopes, the resolution is actually far greater than that. And you can see some examples there of SEM images of single bacterial cells on the surface of inorganic materials.